Hello, this section is on solving exponential and logarithmic equations. So first we're just going to start by looking at some logarithmic equations, and these ones will specifically have the same base. So very similar to solving exponential equations, we first want to get to the same base, and then we could compare it from there. So in logarithmic equations, once you're at the point where you have one term and another term, well, we know log 2, 72, must equal to log 2, 12 plus 2x, and therefore these two numbers must be the same. Since we're dealing with the same base, then these two numbers must be the same. So we could kind of ignore the log 2 from this point onwards, and we just know that 72 must equal to 12 plus 2x because the base is the same. And at this point, it's just simple algebra to solve for the x. So first, we're just going to move the 12 over. That equals to 2x. So this gives us 60 equals to 2x. Divide both sides by 2. So we're left with 30 equals 2x. Actually, I'm just going to rotate around. I'm more used to looking at the x on the left side there. Okay. And there's our first scenario. Now next, let's add a bit more complexity to it. So now we have a couple more terms. Again, we want to get it to the point where we just have one log term on one side and another on the other side. Right now we have kind of two, but we can easily combine it because now we have those laws of logarithms in our minds, right? Since we have same base subtracted, we can just use the quotient law. So that'll be log 7 2x plus 2 divided by x minus 1. And on the other side, we just have that same thing, no change there. And since, again, we have just one log term equals another one, and we're looking at the same base, we know this kind of number portion must be equal. So we could, again, just take out that log, and we know that these two are the same. At this point, it's just a matter of moving things around to solve for x. So since we're dealing with a fraction here, let's just multiply both sides by our denominator so we can get rid of that. So we'll multiply by x minus 1. So now this is gone. So we have 2x plus 2 equals 2. I'm just going to multiply this out since we have difference of squares. Since we're looking at quadratic, it's always a good idea to move everything to one side. So I'm going to move the 2 and the 2x over. So we have 0 x squared minus 2x minus 3. And here we can see that, hey, we can factor this thing. So it's x minus 3, x plus 1. And from here we can see this left bracket here, x is basically equal to 3, and here x is equal to -1. Now, for these particular equations, we do have to do something that we sometimes do with other equations, which is, it is important to check. So we have our 2, let's just take a look. So for 3, again, with the number you get, just plug it back into the original. So we have log 7 2, 3 plus 2 minus log 7 x minus, oops, not x, 3 minus 1 equals to log 7 3 plus 1. Let's put these numbers together. So log 7, we have 6 plus 2, so that's 8. And then we have minus log 7. 3 minus 1, that's 2. And log 7, 3 plus 1, that's 4. Since we have a difference, or we're subtracting here, we can just use the quotient law. 7, 8 divided by 2 equals to log 7, 4. So we have log 7, 4 equals to log 7, 4. Since the left side equals the right side, we're okay with x equals to 3. Now let's take a look at the next one. When x equals to -1, we have log 7 to -1 plus 2 minus log 7 -1 minus 1 equals to log 7 -1 plus 1. And when we kind of simplify this, we have log 7 -2 plus 2, that's 0, minus log 7 -2 equals to log 7, 0. So at this point, I'm just going to put a bracket around that -2. You'll see that we have some issues here. Because as we know, when you have a base of something, no matter what number the exponent is with a base 7, there's no way you can get 0. And if you have a base 7, there's also no way you can get a negative number. So this means that x equals to -1 isn't going to work out. So in this particular case, we only have one solution, and that is x equals to 3. All right, on to our third question now. So here we have log x plus 1 squared equals to 2. Since there is no base, remember this is our common log, so we're looking at a base 10. And on this other side here, we don't have a log, we just have a number. But in order to compare the two sides, we do need to work with the same log. So we'll need to rewrite this 2. Now, if you think about it, what will equal to 2? So if we have log 10, basically, what's our number that will equal to 2? Well, we know that base 10 to our exponent will give us that number in our box. So it's 10 to the 2. I'm just going to write that. So we know that actually has the same kind of amount here. So 2 is just equal to log 10, 10 to the 2. So let's just put that into our equation. So we have log x plus 1 squared equals to log 10 squared. So now we can make the two sides equal since we're working with the same log with the same base. So we have x plus 1 squared equals to 10 to the 2. We want to isolate that x by itself. I'm going to square root both sides. So we have plus minus. So we're looking at x plus 1 equals to 10. So we have x equals to 9, and we have x plus, negative. X plus 1 equals to 10. So we know x can also be negative 11. Again, we do need to check. Okay. So first we have x equals to 9. So we have, but when we're checking, there's one thing we do need to be careful of, I need to point that out, is the fact that when you're looking at a kind of a number here, on this side here, that is squared, when you're doing the check, you do need to expand that. So when you think about it, this is actually log x plus 1 times x plus 1. When this term here can be multiplied, you can open that up with the product law, right? So I'm just going to write a note here. Expand when checking, okay? So while we're checking it, we have to expand it. So it's actually log x plus 1 plus log x plus 1, and that equals to 2. So if x equals to 9, we basically have log 10 plus log 10 equals to 2. So log base 10 is basically just 1 plus 1 equals to 2. So 2 equals to 2. We're good. Now if we have negative 11, we have log negative 11 plus 1 plus log negative 11 plus 1 equals to 2. And if you kind of simplify that, we have log negative 10, log negative 10 equals to 2. At this point, we can stop because we can see our log is giving us a negative number. It's just not going to work out. Nope. Therefore, our only solution here is x equals to 9, and we'll put a box around that. So please be mindful. I'm going to write this in green. Don't keep it together. Okay, so when you have that, you, at least for this part, I'm going to write that here. When you're looking at x equals to negative 11, one thing you don't want to do is to just keep it in the square. So you basically have log negative 10 squared, and then if you just keep on going, we have log 100, and you're like, hey, it totally works. So you do need to break that up. Otherwise, you do see that it works when it doesn't. All right, so next, we've looked at examples with the same base. Now we're going to look at different base. Since we have a different base, the first thing we need to do is change the base. So with these questions, you want to change that bigger base to the smaller one. So we're going to leave the base with the smaller number as is. With the bigger base, we're kind of going to use that change in base kind of formula that we have. So we're going to have log to our number over log of the base. And we can pick whatever base we want as long as it's the same. Since we're changing to the base 5, we're going to have both of them at log 5, and that equals to 10. So as we know, log 5 to the power of what gives us 25? Well, we know this part, that equals to 2. So let's just write that out. Log 5x minus log 5, x over 2 equals to 10. Since we have the denominator of 2, let's just multiply everything by 2 so we don't have to worry about a denominator anymore. So I'm just going to say this whole thing is multiplied by 2, everything. So that'll give us, so that'll give us 6 log 5x minus log 5x equals to 10. Oops, not 10, 20. Okay. And here, when you, since we have the same base, we can kind of just put it together. So we basically have 6. I'm just going to use the power law to put it back. 5x6 minus log 5x equals to 20. So from here we have log 5x to the 6 divided by x equals to 20. So therefore we have log 5x to the 6. Not x to the 5 equals to 20. I'm going to use the power law and just move that 5 back out. So 5 log 5 x equals to 20. I'm going to divide my coefficient away to get rid of that 5. So we're left with log 5x equals to 4. Now this becomes quite the simplistic log equation that we could quite easily solve. If we change this back to exponential form, that gives us 5 to the 4 gives us x. And when you punch that into the calculator, you will know that it is x equals to 625. Okay, so some of you, without having to do all these kind of steps in between, you might see, hey, log 5, when you have 6 log 5x, log 5x, these two are basically the same, but here we have 6 of them, here we have 1 of them, so this already, you can already see that you have 5 of them left. So some of you may have easily skipped from this step straight to this step here directly on the right. But if you weren't able to see it, this kind of step in between is fine as well. All right, so here's the exponential equation part and how it ties up with logarithms. So when we were looking at exponential equations before, usually they were easier to solve, and sometimes when we just couldn't find those perfect numbers to root, then we would have to guess and test. But now with logs, we can find much more specific and exact values. We don't have to guess and test anymore. We know exactly what it will be. So here we go. Here's a question. We are not really sure. Can't really figure this out with just numbers we may know. So we will need to bring in log. So at this point, we'll just log both sides. It's kind of like when you're using exponents, you just kind of square both sides kind of deal. Same idea. So we're just going to log both sides. So we have 7 2/3 x, this is an exponent, equals to log 40. With the power law, we're just going to move everything out. So we have 2/3x log 7 equals to log 40. Now we can kind of just divide both sides by log 7 because it's those two multiply. So log 7 is gone. So therefore we have 2/3x equals to log 40 over log 7. So now we're just going to, need to isolate x. So I'll just draw an arrow here. Isolate x. So we need to divide the other side. Divide the side with the logs. Divide it by 2/3. So at this point, you can just use your calculator. So we have log 40 divided by log 7 divided by 2/3. And this, you should get 2.84. Okay, so I mean, there are many more decimals. Let's just round to the nearest hundredth here, okay? All right, next question. So here we have this question here. Well, before we just start logging everything, it's always good to just simplify things first. And before we just dive right in, well, both sides could be divided by 3. So let's just simplify as much we can. So 52 is, we can't divide that as is. Sorry. So it'll just have to stay. So the 3 is gone, and we're left with 2x equals to 52/3. Ooh, we can't just do this one in our head, so we'll need to bring out that log. So very similar to last time, log 2 to the x equals to log 52/3. We're going to use the power law to bring that x to the front by itself, and then we have log 52/3. We'll need to isolate that x by itself and divide both sides by log 2. Let's just write that down here. That's gone. So we basically have log 52/3 over log 2. Now sometimes for some questions, I may just ask for you to answer in terms of log. So answer in terms of log. And when you see that, basically this is the point in which you'll just have to leave your answer, when you can't simplify it anymore. And at this point, to find your solution, all you can do is punch it into the calculator. So when I say answer in terms of log, this part is when you'll stop. But if I do want an answer, you'll need to punch it into your calculator. So it's log 52 divided by 3 divided by log 2. And you should get to a final answer, if you're rounding it to the nearest hundredth, 4.12. That'll be to the nearest hundredth or 2 decimal places. All right, last question here. So this one here, can we simplify it anymore? No, we cannot. Let's just log it then. So we have log 5x equals to log 2x plus 1. So let's just move the x's to the front. So we have log 5 equals to x plus 1 log 2. Now here's the part that is a little different. So instead of just kind of dividing both sides by 2, we do want to somehow isolate those x's by itself, but right now we can't. So what we'll actually have to do is we'll actually need to expand that right side there. So we'll have x log 5, but we're going to multiply out this side here. So we'll have x log 2 plus log 2. Now we have those x's kind of isolated on its own, so we're going to move them all to one side. Everything with x will move to one side. Minus x log 2 equals to log 2. And we're going to factor out that x, so it could be all by itself. So log 5 minus log 2 equals to log 2. And to get the x by itself, we'll have to divide both sides by log 5 divided by log 2 divided by log 5 minus log 2. So these are gone. So we know, I'm going to draw an arrow again, x equals to log 2 divided by log 5 minus log 2. If you want, again, if I ask to leave it in terms of log, this is kind of as far as you can get. If you would like, you can also have it use the quotient law. Use the quotient law for the denominator and kind of have it like so. Okay, so both ways could work if I asked answer in terms of log. But if I want an actual number, you'll need to, again, punch into your calculator. So that's log 2 divided by log 5 divided by 2. And that will give you, again, to the nearest hundredth, 0.76. Okay? And that's it for exponential and logarithmic equations.